In this lecture we are going to talk about the determinant. So what is the determinant as a mathematical object? As a mathematical object, the determinant is a function which we will denote by that n, going from the set of matrices, n by n matrices, to the real numbers. So it will take a matrix and will give you back a real number. But since the set of matrices can be identified by a bijection, canonical bijection to the set of column vectors of Rn, in which way? Well, we take a matrix, and to a matrix we associate the set of its column vectors. Each column vector of an n by n matrix is going to be a vector in Rn, written vertically. So we can associate the C1 as the first column, C2 the second column, comma, so on, comma, Cn the nth column. So we have n column vectors here which are associated to the matrix we are starting from. The same goes for row vectors. So we can take a matrix and associate its row vectors, and we end up to with an n-tuple of vectors in Rn written horizontally, R1 up to Rn. And vice versa, we can associate the matrix comprising these row vectors and the matrix comprising these column vectors. So these are bijections. Why do we even want to talk about the determinant? Well, the relevance of the determinant is that it detects invertibility of matrices. More precisely, a matrix has determinant different from 0 if and only if M is invertible. Okay, so to check whether M is invertible, we have two options usually. One is to if we know that somehow it is invertible, to present its inverse. Okay, so if we say, look, I show you that M is invertible because this one I write you down is its inverse, then, well, that is a proof that M is invertible because you presented its inverse. Otherwise, we can use this theorem that we will state with much more details in future lectures, and compute the determinant of M and show that this determinant is non-zero. Okay, this is going to show that M has an inverse matrix, so it is invertible, although we will not have constructed it. Okay. Moreover, there is an algorithm computing the determinant of M, so it's not just something abstractly defined. Now notice that a determinant of M provides a way of showing that the matrix is invertible without finding the inverse matrix, as we just stated before. Now, before defining the determinant of N, which will happen in the next lecture, we list its determining properties. 1, 2, 3, and 4. What does that mean? Well, it means precisely what the following theorem states. Theorem: there exists only one function going from the set of column vectors in Rn to R, satisfying the properties that we are going to list now, 1 through 4. And this function is what we will call the determinant. Okay? So there will be just one, and this theorem is especially important to prove certain properties of the determinant, as we will see in the future lectures. Now, in order to state the properties, let me introduce this notation. So V1 through Vn will denote column vectors of Rn, W will be again another column vector of Rn, and lambda a scalar in R. So the properties will be stated exactly in these terms. So we will see the determinant acting on column vectors instead of matrices. So the first property is the one that maybe is a little harder to state. So the element to which we apply the determinant is the n-tuple of column vectors given by V1, V2, so on until the ith column vector, which by assumption we write as a sum of two vectors, namely vector vi and vector w. Okay, so the ith column vector will be vi plus w. And then we resume with the usual notation of vi plus 1 through vn for the remaining arguments of the determinant. Now the property states that the determinant of this n-tuple of vectors is going to be the sum of two determinants. The first one being of the n-tuple given by v1 through vi and then through vn. Basically, in the ith position, I no longer have two vectors here, but just have one vector corresponding to the first summoned, vi. The second determinant will be applied to the following n column vectors. Again, the ones outside the ith position will remain the same, so v1, v2, and so on. The ith column vector, which in this case is going to be w, corresponding to the second summand of the ith column vector of the first determinant here. It is like splitting these two summands in two summands of determinants. The first one involving vi and the second one involving w in the ith position. And this, of course, must hold for every I. So for every argument, I just picked one and I called it I, but this property has to hold for every argument of the determinant. So there are n of them here. Second property is regarding, instead of regarding the sum of two vectors, it regards the other structure of vector space, which is multiplication of vectors by scalars. Therefore, the ith vector here, instead of being a sum of two vectors, is going to be one vector vi multiplied by a scalar lambda, whereas all the other arguments, all the other vectors, are just the ordinary, denoted by the ordinary vi's. Now the property states that this lambda coefficient can actually be pulled out of the function and put it and placed it in front of the function. Okay, so as you notice here, the right hand side of the equality, we have first a lambda and then the determinant of what remains inside of all the arguments, which is v1 through vi minus 1, and then the ith column vector, what it remains is just vi, and so on through vn. Okay, so lambda, the scalars, just pass through all the arguments and go in front of the determinant. And once again, this property has to hold for every I. The third property regards the situation in which out of the n column vectors to which we apply determinant of n, there are two of them consecutive which are equal. Here I named w, the one in the ith position, and the one in the I plus 1. So I'm assuming both of them to be equal to w. Now the property says that, well, in this case the determinant has to vanish, must be equal to 0. The last property is stating that the determinant of the identity matrix must be equal to 1. Now, what is the identity matrix in the context of column vectors? Well, by the correspondence that we stated before, we have to associate to identity matrix its column vectors. Therefore, the first vector will be 1 and then zeros, and the second column vector will be 0, 1, and then zeros, and so on. The last column vector will be zeros up to the last scalar, which will be 1. Let's now give some names to these properties. Now, properties 1 and 2 are called the n multilinearity structure or property of the determinant. Why is that? Well, linearity in general, as we will see in the next lectures of the course, linearity of a function regards the behavior of the function with respect of the vector space structures. So summation of vectors and multiplication of vectors with the scalars. And here we have precisely this, but it just regards one of the n arguments of the function determinant n. Now, if these linearity properties regard all of the n arguments, then we are talking about n multilinearity. So multilinearity because it is linear in each of the arguments, and the arguments are more than one. N multilinearity, well, n specifies the number of arguments that this function has. Now, property 3 is called the alternating property. And if we know that the function is n multilinear, then the alternating property is equivalent to the following one. So if we apply determinant to any matrix, and then we compute the determinant of the same matrix in which we have switched the order of two vectors. So in this case, the n vectors, the column vectors that we have here on the left, they have a vi vector in position I and vi plus 1 in position I plus 1. Well, the vectors here on the right hand side, they have switched place. So in the ith position we have vi plus 1, and the ith plus 1 position we have vi. So if we switch the order of two of the arguments of the determinant, well, the determinant will change sign, will pick up a minus here in front. So in the case of multilinear maps, this property is equivalent to the one stated in number 3. Namely, the determinant is 0 when two consecutive vectors are equal. I'm going to finish the lecture with the proof of the theorem we just stated before. In the special case n equals to 2, I remind you that the theorem stated that there is only one function satisfying all the four properties that we just stated. So let's verify these in the special case n equals to 2. We write f as a function satisfying properties 1 through 4, and we are going to compute f applied to a generic matrix. Let's call this matrix through the coefficients, its coefficients. So we have a, b, and c, d. Now, how do we express the matrix in terms of column vectors? Well, f then will be acting on the pair of column vectors given by the first column AC and the second column BD. Now we write the first argument of the function f, namely the column vector AC, as a sum of two vectors in order to apply property 1, which dealt precisely with this situation. So the vector AC can be written as the vector A0 plus 0C by definition of sum of two column vectors in R2. That was component-wise sum. Okay. So applying property 1 to this pair of vectors, of which the first one is a sum of two vectors, precisely the property 1 precisely implies that the f of this pair is going to be the sum of 2f. Now next step will be writing vector A0 as a product of one scalar times a vector. Now A0 is clearly A times 1, 0. The same goes for 0C, which is C times 0, 1. And then we can apply property 2. Now property 2, in this case, states that we can pull out from the arguments of f the coefficients. So in this case, in the first summand, the coefficient is a. So the first summand is going to be a times f of the remaining arguments, 1, 0, comma bd. And the second summand, we can pull out c, and what remains is f of 0, 1, comma bd. We can no longer proceed considering just the first arguments of f, because we can no longer reduce the vector 1, 0 and 0, 1. Therefore, we bring our attention to the second arguments, which are the same because we never touched the second argument in all this process. The second argument always remained the vector BD, but of course we can repeat the same procedures, just leaving untouched the first of the arguments and applying the same procedure to the second argument. Now, instead of having just one f, now we have two f's, so two summands, and we apply the same procedure to each of the summands. So remember that the first step that was here involved writing the column vectors as a sum of two vectors. Okay, so we do the same here. So BD will be written as B0 plus 0D in both cases. And then after we split the column vector as a sum of two vectors, we apply property 1. So we do this at once here. So applying property 1, splitting BD in B0 plus 0D and applying property 1, we end up precisely with these two big sums, one corresponding to the first summand and the second one corresponding to the second summand. What was the next step before? Well, the next step involved property 2, which meant writing vectors as a scalar times some other vector. So A0 is A times 1, 0, and 0C was C times 0, 1. Now, in this case, what do we have? We have as vectors B0 and 0D. So we can write B0 as B times 1, 0, and 0D as D times 0, 1. And applying property 2, these coefficients, B here and D here, will be taken outside F. So what do we get? Next step, we have equality. By property 2, we have A times. So we have two summands. The first summand is B times F of what it remains. So 1, 0, comma 1, 0. B0 was B times 1, 0, so it remains 1, 0. And then second summand, it will be D times F of 1, 0, and then 0D, it remains 0, 1. And then here in the C summand, we have first B coming out of F, and then D again coming out of F. There are a few things you can simplify here, applying property 3 now. Because as you see here we have f of 1, 0, 1, 0, and the property 3 precisely stated that when we apply a function to an n-tuple of vectors and two consecutive vectors are equal, then f will be 0. Okay. So here we have just two vectors, and both of them are equal to 1, 0, therefore they are equal. And so f of this pair of vectors will be 0. For the same reason, this one will be 0. So what remains at the end are just two summands. Now next step, so we rewrite the two summands which remain out of all this expression. So we have A times D times f of 1, 0, 0, 1 plus C times B times f of 0, 1 and 1, 0. Now these two real numbers, f of 1, 0 and 0, 1 and f of 0, 1 and 1, 0, are actually related one to the other. Why? Because we apply again property 3, but in the equivalent form that we have written before. So you remember, as it was originally stated, the alternating property said that if two consecutive vectors are equal, then f is 0. Now the alternative version was if two consecutive vectors are being switched, then f changes sign. Okay. Now as we can see here, we have f applied to two vectors, which in one case are 1, 0 and 0, 1, but in the second case they are the same vectors which we have just switched the order. But f of 1, 0, 0, 1 is again something we are familiar with, because that is precisely property 4. Property 4 states that the f of the identity matrix is going to be 1. Okay? So in this case, we precisely have here identity matrix. We have the column vectors of identity matrix, 1, 0, and 0, 1. Therefore, this f equals 1, and this f equals to minus 1. Summing up, we end up with the following expression, AD minus CB. So as we see, after having used all the properties 1 through 4, the f applied to the matrix ABCD necessarily will have to be equal to the following expression, A times D minus B times C. So there is no other possible definition of f if f satisfies 1 through 4 property. Okay, so this shows that there is just one f, and this f must have this expression in order to satisfy all these 4 properties. And this is precisely the determinant of a 2 by 2 matrix.